So let's start with what is given to us. And it could be, like in this example, pretty simple. The only information we're given, really, is the diagram. There's no extra stuff. So given step, done. Find step. In this case, it's pretty explicit what we want to find, but there could be other problems where it's a little bit more vague, or we have to investigate from the word problem how to translate that into quantities we want to find. So even though it's obvious, what do we want to find in this problem? Right, so there are the tensions in those two cables. I'm going to call them TAB, TBC. You could name them whatever you want. Here, it was given to us so we know what we're looking for. So two things we want to know. They're both forces, and we know they're both in tension. So now a crucial step, maybe the most important step of this process, the free body diagram. So in particle equilibrium, it needs four things. So we have to start with an object, or in this case, a particle of interest. What particle are we taking and isolating from the rest of the system, and then putting all the forces that act on it? So remember, so when we pick our particle, we have to remember what are we ultimately looking for, and that will influence the particle that we choose. So this one is fairly obvious, but what particle should we isolate from everything that's attached to? Right, so that ring at B. So that ring is a 3D object. For this chapter, we're simplifying it down to a single particle. For particle equilibrium, what that means is all forces act concurrently, which means all forces act through that point. When we get to chapter 4 and 5 and beyond, when we have rigid bodies, that's no longer true. So to simplify this, we represent that ring as just one dot. Object of interest, well, we could try out after we draw it that that's not the right particle of interest, or we might have multiple ones. So we can start there as a first step. Next thing we need for a free body diagram is we need a right-handed coordinate system. None is given to us, so I'm going to go with the simplest one possible. X right, Y up. Even though that's the most common and probably most of what you do will be X right, Y up, you must include it in the picture or your equation steps don't mean anything. So here I explicitly labeled X right, Y up. You can also put to the side something like this. As long as there's a clear indication of what your coordinate system is, that's the important part. All right, so right-hand coordinate system, done. Now we have to represent all of the forces that are acting on this particle. So again, we cut it away from the ropes, so we have to put in what are the forces in those ropes in this picture, and they're correct, well, if we know the direction, the correct direction. So what forces and how do I draw them on this picture act on point B? Yeah.
You have 200 pounds going straight down.
Right, so that motor has a weight of 200 pounds. The rope it's attached to, therefore, has a tension of 200 pounds. So we can represent that, cutting away that rope, the force that rope exerts on particle B is 200 pounds straight down. Right, so the rope is not in the picture, but the force that the rope exerts on B is on the picture. We're only drawing what do all of these things do to the object, not what does the object do to these other things. So this thing pulls, this force alone pulls our object down. Right, what other forces are acting on our object?
You have the tension from BA and BC at the given degrees.
Right, so we know that forces in ropes and cables always act along those ropes and cables. So when we cut away rope BC, we'll replace it with the force that rope exerted on the particle, which I'll call TBC. I know it has to be a tension because this rope can only exert a tension. It can only pull on objects, it cannot push on them. And we know that it's directed along that rope, so it's also at 20 degrees. Same is true for AB. It has to act along rope AB, so it has to act along 40 degrees. I don't know what the force in these cables is. That's why I'm labeling it as a variable, but I do know their direction. So I've also taken care of the fourth requirement for the free body diagram, dimensions. 40 degrees from the negative x, 20 degrees from the positive x. Everything is dimensioned, everything is labeled, coordinate system, object of interest. So now I have a complete free body diagram for this problem. Questions on drawing the free body diagram? This leads me into the next step, the equation step. So every free body diagram I draw will lead me to equilibrium equations. This is in equilibrium, so I know that I can say that if I sum all the forces in the x, it has to be equal to 0 because the acceleration in the x is 0. So really this is similar to what we did last week when we were summing our forces together and getting a resultant force. This is a little bit easier in some respects because we know the resultant. We already know the resultant is 0. So really the only part of this we're constructing is that other side, what are the sum of all the forces? And we get that from our free body diagram. So in the x direction, what forces act along the x direction?
Cosine of 20 degrees and cosine of 40 degrees.
So, well, a little bit more than that. Those are how we get those components. Yeah.
It would be the cosine of, for TBC, it would be cosine of 20 TBCX.
Right. So all right. We'll take it one step at a time here. So TBC acts both in the x and the y direction. For this equation number 1, we only want to know how much of any of our forces act in the x direction. So TBC, we only want, really, I'm not writing with i's and j's. When we get to 3D equilibrium, I will. Really what I'm writing there is only I components of forces. So the I component of the TBC force is TBC cosine 20 degrees. So that's all of, so I don't know what the magnitude is, but I know that direction. What else do I need in this equation? Yeah.
You have to add the TAB cosine 40.
Right, so the horizontal component is TAB cosine 40. So what's missing from the equation? Right, so which should it be? Right, so here, TBC, this goes back to what we talked about last week. This component is in the positive x direction, but for TAB, its horizontal component, I'm not going to draw this in the future, but its horizontal component points to the left, which I've defined as the negative x direction. So in this equation, this has a negative component, a negative I component, this had the positive I component. And finally, we have that third force. How much of the 200-pound force acts in the x direction? Right, 0, it's along the y, so it will not appear in the first equation at all. All right, so I have one equation. I have two things I don't know. So right now I can't solve numerically for anything. So at the moment, I'll put this equation aside, and I'll move on to my second equation. So I always have in particle equilibrium, two linearly independent equations. So now I shift my attention to y, or really the j components of all my forces. So looking at TBC, its j component is TBC sine 20, because that's going to be the vertical leg of TBC. And then what else do I include in this?
You add TAB sine of 40.
Right, so here the j component of TAB is positive. So this component's positive, this one's also positive. It can also, in 2D, it's easier if you look at what quadrant they're in. That will tell you should the components be positive or negative. And then what else do I need in my second equation? Yeah.
Minus 200 pounds.
Right, so that now the weight force comes down. I drew it down. It's in the negative y direction, so it's negative here. All right, so looking at my equation step, I now have two linearly independent equations. If I count my total unknowns, I have two unknowns, both of which are in both equations. I now know I have a solvable system. I also want to look at my find step. The two things I want to find are both in my equations, so I know that I will also be able to find, ultimately what I'm looking for, those two tensions. All right, questions on the equation step? Generally, it's in the tidbits part. Like the mass of the ropes, I'm not including in this because they're very small. usually compared to like the weight of that motor. They're also very small compared to the other forces that are in them. So usually the weights of members are neglected. And the weight of the ring itself, we also presume is very small compared to the forces that are acting on it. All right, so now the solve step. So I take the equations, and now I want numeric values for them. So I have two equations, two unknowns, a 2x2 system. So what I can do is rearrange equation 1. I can say that TBC is equal to TAB cosine 40 over cosine 20. So like I did last week, I'm isolating one of my unknowns, namely the TBC. And I can get a decimal value for this, which will be easier to work with. So that's going to be 0.815 TAB. I label it 1.1 because it's not a new equation. I'm just rewriting one I already had. So I don't want to make it look like I have more independent equations than I really do. I can take that and I can now put it into what I'll call 2.1. I can use this rule everywhere I see TBC. I can use this definition. So instead of TBC, I have 0.815 TAB quantity times sine 20 plus TAB sine 40 minus 200 equals 0. So in equation 2.1, what I've done is I now have only one unknown in the equation, so I can solve this for my unknown. So solving this for my one unknown, the tension in rope AB, I get 217 pounds, which is one thing I was asked to find. If I now go back up, put that back into equation 1.1, put the 217 in for TAB, the tension in BC is going to be 177 pounds.